Building robots for research and development or just for fun is a costly and time-consuming task. If the mechanical base of the robot is not properly designed and built, it can lead to poor results from sensors for navigation or any manipulation hardware attached to the base. In this video tutorial, which is the first part of a series of videos on building a low-cost autonomous robot, I share the design of a large four-wheeled robot that has been realized by using components from two old self-balancing scooters. For electronics and software setup, please watch videos I will post in the coming days. To make sure you do not miss those videos, please subscribe and like the channel. The robot I am talking about is approximately 1 meter long and 600 millimeters wide. The main body is shaped like a rectangular box as shown with dimensions in this visual. The wheels are 400 millimeters in diameter, giving the robot large floor clearance and higher top speed. The dimensions shown are approximate. Here we see two low-cost self-balancing scooters. These scooters were picked up from a local online marketplace and ripped to remove the wheel and motor assemblies. When new, these scooters are sold with the specifications as shown. The load carrying capacity of 100 kilograms for a max speed of 20 km/h makes these scooter ideal for low-cost robot build. At least, this is what inspired me to build this robot. The first step in making the robot chassis is to isolate the scooter chassis and other components from the scooter. We are only interested in the motor assemblies and motor drivers. The balance controller, user interface, and the handlebar are not needed for this project but may be used in some other projects. Once the motor assemblies are isolated, they need to be aligned and placed either with motors facing down or up. We place the motors facing up to get more floor clearance and protect the motors from ingress from the bottom side of the robot. This configuration will also create less bending in the steel plate, connecting the motors together under heavy loads. In this step, both the scooter chassis are joined together to form the robot base that we call the robot chassis. To fill the gap between the scooter chassis, we use a 3 mm steel plate and add steel angle on the sides for strength. The steel plate and angles are welded to the scooter chassis. The robot body consists of a body frame and side and top covers. The body frame is constructed out of 40 by 40 aluminum V-slot extrusions. Approximate dimensions of the extrusions are shown in the visual. It is possible to construct the frame using box extrusion or other profiles, if V-slot extrusion are not available. The side covers are cut from 2 mm thick aluminum sheets in a waterjet cutter. They are attached to the frame using M6 socket headcap screws and T-slot nuts. Now the robot chassis is ready for adding other necessary components. Batteries add most of the weight to the robot, therefore their placement has to be well thought out. We have placed the batteries in the middle to uniformly distribute the load on both front and rear wheels. 4 lead-acid batteries have a combined weight of 21 kilograms, which is close to the 8 lead-acid batteries that both the scooters originally had. The batteries must be secured in place to make sure they don't move around, especially in sudden start or stop conditions. Therefore, an additional aluminum extrusion is used to provide support for batteries from the top. 4 MDF plates are used to mount electronics components such as motor drivers, fuse box, microcontroller board and computers. The battery top aluminum extrusion is held in place by corner brackets and two 3D printed brackets, called contact brackets. The contact brackets provide a soft contact area on the top of the batteries. The horizontal and vertical MDF plates are also mounted with the help of corner brackets. With the addition of the MDF plates, the robot body is sectioned into 3 compartments. The plexiglass top cover is divided into 3 sections for easy cutting in a laser cutter. Another reason for dividing the cover in sections is to allow easy access to individual compartments. The top cover is fixed to the frame using M6 socket headcap screws and T-slot nuts. This illustration shows side panels and an embedded computer mounted on the horizontal MDF plate. Cuts were kept in the side covers to access wiring from the side panels. The side panel body is 3D printed using PLA, while the outside plate is cut from 3 mm thick acrylic sheet. While both side panels are mounted for design symmetry, only one contains the main battery isolation switch, a voltmeter, and charging port. The actual robot is shown here. It is built as per the designs shown in previous visuals however, Some difference are there such as colors and wheel designs. The robot is being tested in a lawn for rotation and linear movements. It shows the speed and dexterity that was expected from the torquey motors and the big wheels. The wheels are not as such off-road wheels, but they show good grip on grass. Currently we are using ROS Noetic and ROS Serial for communication with the Teensy 4.1 microcontroller. All motors are individually controlled and the base uses skid steering for turning. The microcontroller was programmed in Arduino IDE. For the teleoperation we use PS4 controller. A more detailed video on the ROS setup and teleoperation will be part of my next videos. This is a glimpse of the electronic components of the robot. I'll talk about the PCB schematic and motor driver pinout and other electronic design aspects in the next video. To make sure you don't miss the next videos, please subscribe and like the channel. If you have any questions, please post them as comments and I will endeavor to answer as much I could.